Hello friends, welcome to Electrical Design Engineering YouTube channel. This is our lecture number 54 of our free course ETAP. In today's lecture, we are going to study about motor reacceleration after sudden fault. When the sudden fault occurs and the motor after clearing the fault, motor tries to reaccelerate. And we are also seeing effect of the fault clearing time on the motor reacceleration. In this lecture, we will study three cases of motor reacceleration. One is fault is cleared after 0.5 seconds, and second is fault is cleared within 0.1 seconds, and third is the determining actual fault clearing time so that the motor reaccelerates successfully. These are the three case studies which we are going to study in this lecture with help of practical example, with the help of an example. This is our ETAP example which we are discussing from the few lectures when we started the motor reacceleration. From that level point we are discussing this circuit. In the previous lecture we have these loads, these are the loads, and we do not have this induction motor. In the previous lecture I have made this example and I have made this circuit in the previous lecture, that is lecture number 53 and 52. In these lectures we have designed this circuit, but in these lectures these two induction motors, this induction motor and this induction motor was not there. I have deactivated these two loads. Instead of that we are using two induction motors, motor 2 and motor 4, because we are here to study the motor reacceleration after sudden fault. First of all, I will show you the parameters what I have entered in these two motors so that you can enter in your ETAP's circuit, ETAP diagram, ETAP SLD, and this will help you to understand this circuit easily. I can double click on this and go to the nameplate. This is the parameters which I have entered for this motor. You should also keep these parameters so that our results and your results will be same. After that you can go to the impage. This is the parameters. In the impage you can have to enter these lock rotor parameters in your system, and this is the torque parameters. You can enter these parameters in your system. After there is a model. I have prepared the model by clicking on the parameters estimation and tuning, and I have shown already this thing how you can model this circuit diagram, circuit model, how you can prepare the circuit model of an induction motor in previous few lectures. Then we can go move to the inertia, and in inertia you can enter the H is equal to, that is motor inertia in megawatt second per MVA 1, and then go to the load. In the load you can select the polynomial, and after that you can click on the load model and select this load model K1 plus K2 W2, and you will get this data. After that you can click OK. Similarly you can also make this induction motor 4 same. You can directly copy this induction motor here. Here is the circuit breaker. You can double click on the circuit breaker and see the parameters of the circuit breaker. You can also prepare the circuit breaker, model the circuit breaker with same ratings and click OK. After that, when you finish these things, you can go to the transient stability analysis and click on the transit stability analysis. And here is the edit study case. Click on the edit study case. We will take the first, that is fault is cleared after 0.5 seconds. So we can name this study case 0.5 seconds FT bus 7. Then go to the events. In the event, I have taken this event ID. I have shown in various motor reacceleration lectures that how you can add the event here. I will show you here also. You can click here. You can name the event ID and time after which you want to put the fault. I have kept here 1 second. So after 1 second, the we are applying the fault of that means after 1 second of motor is starting, motor is running, system is going normally. After 1 second, the fault occurs. So you can put here the time 1 second and click OK. In that event, you can add here we have two buses, motors on two bus 8 and bus 7. So you can enter bus. You can when you click on the add, you can see here is the device type bus and you have the device ID. You can select the bus. What is the bus number? That is bus number 7 and 8. And then from here you can select the fault. Okay, three-phase fault. Similarly, you can make another event ID, that is fault cleared after 0.5 seconds. And similarly, you can here see we have action. In action we have kept a clear fault. That means when you add here, you can in action you can click and you can select the clear fault and click OK. Okay. Here you can do one thing. You can see in event ID, and this time is after see fault is cleared after the motor is started. After fault occurs after 1 second. Then after 0.5 seconds fault is cleared. That means total time is 1.5 seconds. So you can kept these settings as it is. After that, you can go to this device model and you can select here the model machine large equal to 0. Okay, and kept here based on the motor mechanical load, and select here the dynamic model during simulation, that is based on the motor mechanical load, and click OK. Now your settings are done. One more thing I have changed here is that I have made one more modification in this diagram, in this SLD, that you can see here we have made two configurations. One is normal configuration. When I select the normal configuration, both the circuit breakers are closed. Circuit breakers CB1 and CB2 are closed. But when we select the single out configuration, this circuit breaker becomes open. That is only one circuit. This circuit is charging this whole network. For motor reacceleration, in this example you can put it as a single out. But if you want to know how you can make this configuration, how you can make a two configuration in a single line, in a single SLD, you can comment and I can uh, put a lecture on that. Better is to I can show you, because without that you cannot able to perform this motor reacceleration. So you can click on here. When you click here, you can see here, you can copy, and when you copy, you can show you create one from normal one to normal two. You can create the configuration. Then you can select which circuit breaker. Here I have selected the circuit breaker 2 should remain open in this configuration. In this way, you can create the configuration. And now we are going ready to perform the motor reacceleration. That is, we can select the run transit stability. We can select run. See, we have kept the total acceleration time of 15 seconds. I will show where you can put this. You can select this edit study case, again events. You can add here total simulation time 15 seconds. Okay, and run transit stability. From here you can see your what is happening in the system. When you click on that, you can say after 1 second fault, three phase of fault has happened on bus 7 and bus 8. Then you can click again, fault is cleared 1.5 seconds, 1.5 seconds. Now our simulation has completed. We can now simulation has been completed 15 seconds. Now you can close this and go to the transit stability plotters and click no, because I have already done this. That is why it is coming. Select the bus here and select the voltage here and select both the buses here and click plot. Now you can see here one thing, that voltage, this was the first voltage when system was running normally. After that the fault occurs in 1 second, so that is our system voltage becomes 0, that is our bus voltage becomes 0. After that it rises again, but it does not rise completely. The voltage is not returned to normal value. It is around 68%. I will see in the percentage here. Click OK. Now you can see, use the hairline. You can see around 68.5% of voltage has been built up, not 100%. The reason is why before fault the voltage was 102%, but after the fault and when the fault is cleared, the bus voltage does not return to normal value. The reason is why. What is happens? When this condition occurs, that means our motor has become stalled. This has become stopped. That means our motors has not been reaccelerated. Now we have to find the reason why it happens. See, when induction motor is running normally with a certain load, the motor produces motor torque, which is balances the load torque. Because of this balance, the motor runs at a stable speed. That means when the motor initially was running, his motor torque and load torque are balanced to each other, and with this balancing, the motor runs at a stable or at a constant speed. When the fault happens, the bus voltage becomes 0. I have seen when the fault occurs, the bus voltage becomes 0. The motor torque is directly proportional to the bus voltage, square of the bus voltage. If when voltage is 0, so our motor torque also becomes 0. So during the fault, the motor has no driving torque. That means they do not have a motor torque, because motor torque directly depends on the voltage. During the fault, our voltage becomes 0 and motor torque also becomes 0. So during the fault, the motor torque does not act on the motor. During the fault, now what is happening during the fault? Load remains connected. That means load torque is acting during the fault. When fault occurs, during the fault, till the fault remains, load is connected to the system, load is connected to the motors. So that means due to more inertia of the motor, load torque is constantly acting on the motor, but motor torque is 0. So the balance between load torque and motor torque becomes disturbed. Load torque becomes greater than the driving torque, that is the motor torque. This means the net torque, that is motor torque minus the load torque, becomes negative, because at this point the load torque is greater than the motor torque. So our net torque becomes negative. The motor starts to deaccelerate. When net torque becomes negative, so our motor starts to deaccelerate. Now what happens after the fault is cleared? When the protection system removes the fault, voltage returns, voltage comes back, motor starts rising again, motor torque starts rising again. Okay, The motor will try to reaccelerate back to its normal speed. This is called the motor reacceleration. But this is only possible if motor speed has not fallen too much during the fault. If the motor torque has fallen very little, it is around the same value it was before the fault, then the motor reaccelerates successfully. But if it's too much, but if the speed has fallen too much, slip increase. When the speed of the motor falls, the slip increases because our slip is equal to ns minus nr divided by ns. That means when the motor torque decreases, our slip increases, which results in drawing a heavy current from the source to regain the speed. So motor is drawing a heavy current from the source to so that he can regain its speed. He can decrease the slip. This heavy current will cause further voltage drop. We know as the current increase that there is a resistance also in the system. With this heavy current increase, with the increasing of the current, our voltage drops, and our motor torque is directly dependent on the voltage. As the voltage drops, which results in the further decrease in the motor torque. Now the motor has entered in the cascading effect. He is trying to regain its speed, but due to voltage drop, motor torque is going decrease and decrease, and slip is going to increase and increase finally, which results in the stalling and stopping of the motor. This was the case first. That is when the fault is cleared after 0.5 seconds. With the help of graph, we have seen this. You can see also one more thing. I can select here the induction machine and select both the motors, and here I can select the slip. I can close this graph and plot. You can see as the fault occurs, and after 1 second the slip increases abruptly and constantly going on increasing. That what I am saying, that as the slip increases, our voltage drop gets decrease, and finally our induction motor stops. You can also see this with the help of here. I can run one more time this transient stability calculation. See one thing here. You should put your eyes here on this bus. See what is the first of all, what is the voltage here? 102.4% when system is running normally. Now I fault occurs. At 1 second the fault occurs. You can see the bus voltage here is 0 and motor is still running. RPM is there, motor is still running. Due to low torque, because low torque is acting, motor is still running, but bus voltage has 0. Now when the fault is cleared, at this time you can see our motor torque has decreased, motor speed has decreased, that is slip has increased. Now you can do one thing. I can go as much I can move forward, you can see the motor torque is decreasing constantly, motor speed is decreasing constantly. That is low. Our net torque is becoming more and more negative, and our voltage drop is going continuously, dropping continuously. You can see these 2 pointers. You can keep in look here. You can see as I move, the more voltage drops continuously, and motor speed also gets continuously dropped. So slip increases. You can see, see, and finally after 15 seconds you can see our bus voltage has dropped to 68.4% only. That is almost 32% voltage drop has dropped here, and our speed has also dropped, and finally the motors get us stalled. I have shown also through this circuit diagram to you this thing. Now in the next lecture we will see the remaining two motor reacceleration cases, that is fault is cleared after 0.1 second, and uh, to determine the actual fault clearing time. so that our motors can reaccelerate successfully. Thank you.